Hello and welcome back to Biochemistry for Health Sciences channel. In today's video, we shall look at the effect of hypercalcemia on neurons in the brain, causing symptoms such as lethargy as well as fatigue. One of the important skills for healthcare professionals and students today is to be able to explain diseases, the signs and symptoms of diseases at the molecular level. So in today's video, we shall try to explain how hypercalcemia causes lethargy as well as fatigue at the molecular level. Majority of cases with hypercalcemia involve mild hypercalcemia, where the total calcium in the serum is less than 12 milligrams per deciliter. So this is the most common. And in this case, typically these patients do not show any symptoms. However, in some cases where there is moderate to severe hypercalcemia, where the serum concentration of total calcium is greater than 12 milligrams per deciliter, we do see some common symptoms, and then there are some that are much rarer. The symptoms of moderate to severe hypercalcemia include lethargy and fatigue due to the effect of hypercalcemia on neurons in the brain. And then there is muscle weakness due to the effect of hypercalcemia on motor neurons connected to the skeletal muscles. And then there is constipation and stomach pain due to the effect of hypercalcemia on smooth muscles in the GI tract. And then there is urination, frequent urination and thirst due to the effect of hypercalcemia on kidneys. So these are the most common symptoms. If the hypercalcemia involves bone resorption, bone breakdown, then there would be bone pain. Hypercalcemia effect on the heart is rare, and in these cases there could be symptoms such as arrhythmias. So in today's video, we shall look at the molecular explanation of lethargy and fatigue caused by hypercalcemia. In future videos, we'll look at effect on skeletal muscles and then GI tract as well as kidneys. So moderate to severe hypercalcemia will decrease the neuron excitability. It will make it more difficult for neurons to fire, basically to initiate action potentials. And this leads to the symptoms of lethargy and fatigue. So before we discuss how hypercalcemia decreases neuron excitability, it's important for us to have a basic understanding of the resting membrane potential, RMP, as well as the ability of neurons and other excitable cells such as muscle fibers to change their membrane voltage and trigger what we call an electrical impulse or action potential. So neurons, like all other cells, have these very important pumps that use energy, sodium-potassium pumps, as well as potassium leak channels. And with the use of these transport proteins, these cells establish and maintain concentration gradients for various ions. So the sodium-potassium pumps present in cells will kick out 3 sodiums in exchange for 2 potassiums into the cell, and then this potassium will leak out of the cell via potassium leak channels. Chloride typically will follow sodium. So through the actions of these proteins, concentration gradients of sodium, potassium, and chloride are established. So you can see sodium is very high outside the cell, 140 millimolar extracellular sodium, which is basically the serum sodium. Inside the cell, only 10 millimolar. Potassium, opposite. Outside the cell, 5 millimolar. Inside the cell, 140. Chloride, outside 105, inside 5. So you can see there is a concentration gradient of these ions due to the actions of the sodium-potassium pumps and the potassium leak channels. Now, these concentration gradients are very important for the cell's osmotic balance. Okay, so we want to make sure that water doesn't get out of the cell, excessive water doesn't get out, or excessive amounts of water doesn't enter the cell. Okay, in that case, the cell can either shrink or expand in volume, and that can be very bad, very dangerous for the cell, and the cell can die. The concentration gradient, as we shall soon see, is also very important to establish the resting membrane potential and also change the membrane voltage for the cells. Now, the resting membrane potential or resting membrane voltage of neurons, and typically for most excitable cells that has been measured, is around minus 70 millivolts. So the inside of the cell is considered the negative pole, the outside is the positive pole, and the voltage difference between the inside and outside is minus 70 with reference to the inside. There's another term that you should understand, and that's called the equilibrium potential of an ion or an E-ion. So for example, let's consider sodium. So sodium has a higher concentration outside, therefore sodium wants to get into the cell because of the concentration gradient. Remember, everything wants to go from high concentration to low concentration. So this force that is due to the concentration gradient that wants to drive sodium into the cell, this is called the chemical force. Now, as the sodium enters the cell, the outside of the cell, because sodium is positively charged, the outside becomes more and more negative. So eventually it will make it harder for sodium to leave because sodium is positively charged and this outside becomes more and more negative. So remember, opposite charges will attract one another. So this electrical force is going to prevent the sodium from entering the cell. So in this case, the chemical force is going to help sodium enter the cell, while the electrical force is going to prevent the sodium from entering the cell. So when these two forces, the chemical force and electrical force, is equal, there will be no net movement of sodium, and this specific voltage across the membrane at this point is known as the equilibrium potential. So in this case, the equilibrium potential of sodium. So an understanding of the resting membrane potential and the equilibrium potential is important because this helps us understand which ions are responsible for the cell's resting membrane potential, and will also help us understand the mechanism of the electrical impulse or the action potential. Now this equation, called the Nernst equation, translates the concentration difference of an ion into the equilibrium potential. So the equilibrium potential of an ion in millivolts is equal to R, the gas constant, T, temperature, Z is the charge of the ion, F is the Faraday's constant, multiplied by natural log concentration of the ion outside the cell, divided by concentration of ion inside the cell. We plug in the values for R, F and T at 37 Celsius, which is 310 Kelvin. And when we do that, we get the EI in voltage, the equilibrium potential in voltage, and that comes out to be 0.062 divided by the charge of the ion multiplied by log concentration CO outside divided by concentration inside. Notice that we use this 2.303 to convert natural log into log. So if we use the units of millivolts, then this 0.062 becomes 62. So the Nernst equation comes out to be this. EI in millivolts is 62 divided by the charge of the ion multiplied by log of concentration of the ion outside the cell divided by concentration of ion inside the cell. So for sodium, for example, the charge is 1. If we put in the log of sodium outside the cell and inside the cell, outside is 140, inside is 10, and we work this out, it comes out to be plus 71 millivolts. So the equilibrium potential of sodium here is plus 71 millivolts. We do the same thing for potassium, and the equilibrium potential comes out to be minus 90 millivolts. Now for chloride, chloride has a charge of minus 1, so we have a minus 1 here. That will give us minus 62 times log CO over CI. To get rid of this minus sign here, we just flip this CO and CI. So this comes out to be 62 times log concentration inside divided by concentration outside. Plug in the numbers, and for chloride, you get minus 82 millivolts. Another important consideration is the permeability of the cell to various ions. It's been found that the neurons are most permeable to potassium. So the permeability of the neuron to potassium is 1, followed by chloride, which is 0.45, and it is least permeable to sodium, which has a permeability of 0.04. So the resting membrane potential is the weighted average of the equilibrium potential of all permeable ions, especially sodium, potassium, and chloride. And this RMP can be calculated by using the Goldman Hodgkin-Katz equation. So you can see in this equation, we have the 62 over Z, and then we have the permeability of the ion, the concentration of the ion for sodium outside, permeability of potassium, concentration of potassium outside, now permeability of chloride, but because chloride has a charge of minus 1, this is concentration of chloride inside, divided by permeability of sodium, concentration of sodium inside, permeability of potassium, concentration of potassium inside, permeability of chloride, but once again, concentration of chloride outside. We flip that for chloride. Plug in the numbers and you get a value of minus 70 millivolts, which is very close to the measured value of around 70 millivolts. So you may be wondering if the cell is most permeable to potassium, why isn't the resting membrane potential closer to minus 90, which is the equilibrium potential for potassium? Instead, the resting membrane potential, when we measure it, it's minus 70 millivolts. And one reason for this is because of the presence of sodium leak channels, NaLCN. So because of this NaLCN, some of the sodium can actually enter the cell from the outside to the inside along its concentration gradient, And when the sodium ions enter the cell, it will try to make it more positive towards the sodium equilibrium potential of plus 71. So this effect pushes the RMP from minus 90 to something more positive, in this case for most cells to minus 70 millivolts, which is a resting membrane potential. So we can represent the voltage of a cell, the membrane voltage on the y-axis. That's a membrane voltage in millivolts. And on the x-axis, we could show something like time in milliseconds. And around minus 70 here is the resting membrane potential of the cell. So let's follow the changes in the membrane voltage of a typical neuron at rest, and then see what happens when the neuron becomes stimulated and starts firing an action potential. So here's a neuron at rest, RMP minus 70 millivolts. The neurons have receptors connected to ion channels, and these receptors are mostly stimulated by binding of ligands. For example, neurotransmitters may bind these receptors. While there are some receptors that are called mechanoreceptors, and these can be stimulated by physical deformation of membrane. For example, stretching of the membrane or some force that is applied to the membrane. So when these receptors are stimulated, the inside of the neuron becomes slightly more positive. So let's say from minus 70, it might go slightly up to minus 60. And this could be due to events like stimulation of receptors may cause some sodium or some calcium to enter into the neuron via their receptor channels. So now that the voltage has changed from minus 70 to minus 60, now this change will cause voltage-gated sodium channels, NAV, to change their shape, and they will start opening, and when they open, sodium will start entering the cell, thereby making the cell more and more positive. This is called depolarizing the neuron. Now, if the membrane voltage is still less than the threshold, notice the threshold, let's say, is around minus 50, but the membrane potential has not reached the threshold, is still down here, and the stimulation has stopped, or its stimulation is very weak. In this case, nothing happens. The voltage will simply go back down to the resting membrane potential, because remember, the sodium-potassium pumps are working all the time, and they're going to pump this sodium out of the cell. Okay, so they're going to pump this sodium out of the cell, and the resting membrane potential comes back down to the normal of minus 70. However, if there are multiple stimuli happening at various parts of the cell, what we call, and these stimuli happening simultaneously, what we call a spatial summation, or let's say many stimuli arrive at the same location, here, this location here, in rapid succession, very quickly. That's called temporal summation. Then the voltage, the membrane voltage now may exceed the threshold of minus 50. And this is going to cause more and more of these voltage-gated sodium channels to change their shape and start opening. And this opening will cause more sodium to rush into the cell. And now the membrane voltage is going to head towards the equilibrium potential of sodium, which is plus 71. So you can see the membrane voltage is heading towards plus 71, causing the depolarization of the neuron. However, when the voltage reaches around plus 40 millivolts, the sodium channels will close, while the potassium channels will open, And because there's more potassium inside the cell, this potassium will move out from the inside to the outside according to its concentration gradient. And as this positive charge inside, this potassium inside, is lost to the outside, the membrane voltage becomes more and more negative, heading towards the resting membrane potential. This is called repolarization of the neuron. So as the membrane voltage becomes more and more negative, these potassium channels will start closing. Now, these channels close very slowly. Okay, so they are very slow to close. And so the neuron membrane potential goes even less than minus 70 because the channels are closing very slowly. This is called hyperpolarization, when the membrane potential goes even less than the resting membrane potential. So at the end of the action potential, so we have here now at the end of the action potential, there's still appreciable amounts of sodium inside the cell as well as potassium outside the cell. So now the sodium-potassium pumps are working very hard at maximum velocity to try to restore the original concentrations of sodium and potassium. So this part here is known as the refractory period. So this time here, while the sodium-potassium pumps are trying to maintain the original concentration, this is called the refractory period. And during this time, the stimulated region of this neuron cannot fire at all because it is under the refractory period. So this is how a neuron transmits information by using action potentials. So with this background, now we come to the question, how does hypercalcemia decrease the firing by neurons? And the answer is not an easy answer, since extracellular calcium can affect many different proteins inside the neuron as well as outside the neuron. So for example, the calcium in the serum, the extracellular calcium, can bind the extracellular domain of plasma membrane proteins in the neuron, such as ion channels, and this binding can modulate the structures of these proteins, which means their functions can be affected, functions such as binding of ligands, the transport property of these proteins, the opening and closing of the channels, and so on. Now, this serum calcium, this extracellular calcium, may also enter the neurons because there are several different types of calcium permeable channels present in the plasma membrane of neurons. Example, voltage-gated calcium channels, VGCC, acetylcholine nicotinic receptors, and so on. So as this calcium enters the neuron, remember calcium is positively charged. When you bring positive charge into the neuron, you are depolarizing the neuron. So you can change the membrane potential of the neuron. And not only that, this calcium can go and now bind other proteins in the neuron and modulate their functions from the inside. Now, neurons as well as smooth muscle cells, scientists have discovered that they do contain these receptors that we talked about in the earlier video, calcium sensing receptors, which are not so far been detected in skeletal muscles. So this extracellular calcium, the serum calcium, can bind CASRs, and then that will trigger signaling pathways, okay, phospholipase C, cyclic AMP, and these pathways then can go on to affect the functions of various proteins in the neuron. So clearly, extracellular calcium can do many things to neurons, but we'll just look at the major molecular mechanisms reported in literature on how hypercalcemia decreases neuron firing. One is that this hypercalcemia inhibits sodium leak channels. So this high calcium will bind calcium sensing receptors, triggers signaling pathways, and that signaling pathways ends up inhibiting these sodium leak channels. Now remember, as we discussed earlier, because of the sodium leak channels, that's why the membrane potential is minus 70 and not minus 90, closer to the potassium equilibrium potential. So when these channels are inhibited, now the resting membrane potential is going to go even more negative, let's say minus 80 millivolts. So since the resting membrane potential is more negative, it is going to make depolarization even harder. It's going to make reaching threshold even harder, and this will decrease the neuron firing because it's harder to reach threshold. And this will lead to the symptoms of lethargy and fatigue. Another important reason why high calcium makes neurons less excitable is that this calcium inhibits these voltage-gated sodium channels. Okay, so these voltage-gated sodium channels are inhibited. It makes them more difficult to open. And remember, they are responsible for the depolarization part of this curve. This means it will be harder to depolarize and reach threshold. And when it's harder to reach threshold, once again, there will be decreased neuron firing, and that will lead to lethargy and fatigue. Now, there are several other effects that have been reported in literature. For example, the calcium may affect the neurotransmitter release. The calcium may affect many different other channels, proteins present in neuron, such as cyclic nucleotide-gated channels, potassium chain channels, whether they are leak or voltage-gated, and other ligand-gated channels. And all of these effects may lead to the resting membrane potential being changed, the refractory period being affected, and thereby affecting the action potential frequency, and of course the threshold can be affected, thereby reducing the ability of the neuron to fire. So hopefully you have an idea of why hypercalcemia decreases neuron excitability, explained at a molecular level, that then leads to lethargy and fatigue. In the next video, we shall look at how hypercalcemia causes muscle weakness by affecting the motor neurons in skeletal muscles. So until the next video, once again, thank you very much for watching and supporting this channel. Goodbye and have a wonderful day. We'll hopefully see you soon in the next video.